All right, it's 3:10, so let's go ahead and get started. Today we are fortunate to have Matteo Cantiello visiting us from the Center for Computational Astrophysics at the Flatiron Institute, as well as Princeton. Before Matteo was working where he is now, he got his PhD from Utrecht University, and then was followed, did a couple of postdocs in Bonn and at KITP before heading to the CCA. Matteo is an expert in all things theoretical stellar astrophysics, from asteroseismology of low-mass stars up to the evolution of massive stars and binaries. In particular, Matteo's work is really cool because it's at the interface of 3D hydrodynamical simulations and 1D stellar evolution codes like MESA. And another fun fact about Matteo is that he is the Chief Scientific Officer at Athoria. So if you were interested in talking about public journal access and things like that, definitely check him up. He will be visiting for the rest of today as well as part of tomorrow, and we will be going to dinner tonight as well. So let me know if you'd like to join for that.
Amazing. Thank you, Katie. All right. So it's a pleasure to be here. It's my first time at CITA and the first time in Toronto. And I was afraid I will never see the needle. Apparently it was hiding right behind the tower in front of my office. And I was looking around. I couldn't see it. And it turns out it was exactly aligned behind it. So today I want to tell you a little bit about my line of work and how I think relates to the current state of stellar astrophysics. We'll talk about the new era of stellar physics, and I'll explain a little bit in the next few slides what I mean by that. What I mean by that, and what I mean about exciting times for stellar physics. As in many subjects in astrophysics, usually the excitements come when there are new set of observations. And for stars, we live in a particularly fortunate period. There are numerous transient surveys that look for change of things like brightness of stars in the sky, with the aim of finding things like supernovae that in the latest years revealed a number of very interesting transients, type of supernovae that were not predicted theoretically. This definitely made people go back to the blackboard and try to understand what's going on. I know some of you work on a weird type of supernovae and supernovae light curves. At the same time, we were able to witness the entering of a new era of high-precision stellar physics, in particular using missions that look at stars in photometry. The space telescope like Kepler, Bright, and TESS look at a large number of stars and look at the light curve, so the luminosity as function of time with very high precision from space. And that then you'll see in power to apply a very interesting technique called Asteroseismology to a large number of stars. And that can help you revealing details of what happens inside stellar interiors, something I'm particularly interested in. Also Gaia obviously helping because provides a mean to determine distances and therefore absolute luminosities of stars and allows to put stars on theoretical HR diagram with a much higher precision. Well, finally we live in at the dawn of the gravitational wave astronomy era. LIGO and Virgo allows now to routinely identify the remnants of massive star, most likely, that merge and produce gravitational waves that can now be detected at the Earth. As you will see, this is a key aspect of trying to understand the evolution of more massive stars and determining what the final properties of the leftover remnant of the evolution of stars much more massive than the Sun are. And finally, I wanted to mention the idea that we might be close to probing a very early universe, the epoch of reionization, and where this era of the cosmos is very interesting in the context of the first stars, the first massive stars that might have played a role into this reionization. So either you're interested in planet or you're interested in the chemical and dynamical evolution of the gas in a galaxy, or you want to understand the gravitational waves sources of the LIGO, of the detection made by LIGO and Virgo, stars are important. And for the latter two examples, massive stars are of particular importance. In this sense, I think we live in a very special era of stellar physics where I think we're going to there's a role for both observations, 1D stellar modeling, and three-dimensional calculation to come together and provide a synergetic effort into understanding better what happens inside stars and how that impact their evolution and final outcome. And so this synergy is something I've been particularly interested in and I've been working on. And so the rest of the talk is going to be a sort of a showcase of examples where these special feedback loop has led to some interesting new understanding of stars. So I work on modeling stars, and I do computational modeling of stars. And when I tell this to people, and I say that there's still a lot of uncertainties in our understanding of the life and death of stars, people get a little surprised, and they ask me, why don't we just forget about this one-dimensional simple approximation that people have been running for a long time, stellar evolution calculations, where things like convection is approximated with the MLT theory, mixing length theory. Everything doesn't know about turbulence. Everything is very simple. And why don't we just run like a big simulation of a star like the sun, where we include all the three-dimensional physics, rotation, convection, maybe magnetism, and call it a day, see what happens. I want to show you now why this is not going to happen anytime soon. A problem is the hierarchy of time scales and length scales. So in the case of the sun, let's imagine that we want to simulate the sun, and we want to simulate the full dynamics of things like convection in the envelope. So convection is a process that steers the plasma at a certain length scale, comparable to the local pressure scale height, let's say. And we have these large cells that transport energy, and then this energy is kind of decaying down through a turbulence cascade down to the viscous length scale. This is a typical process, and turbulence usually in most environment appears having a spectrum that is a Kolmogorov spectrum. So now if you want to know what's the dynamic range of the length scale that you need to resolve going from the energy injection scale through the inertial scale down to the viscous scale, where your energy is going to dissipate it, well, that relates to the Reynolds number of your flow to the third, fourth power. And in the sun, the number is very large. It's about 10 to the 10, meaning that the ratio between the maximum length scale and the minimum length scale you want to resolve in your flow is about 10 to the 7. Now you can see already a problem emerging. If you want to simulate the sun convection zone, then you want to put the sun in a box, in a three-dimensional box, where the number of cells is about this ratio to the cubic power. So this means that you'll have to have something like 10 to the 22 cells in your simulation in able to capture the full cascade process of turbulence in a simulation of the sun. This is sometimes called a direct numerical simulation, meaning that you are considering all the scales down to the viscous scale. This is a problem, though, because you might know that when you run like a very large simulation, even one of the supercomputers available, this is a picture of the number one ranking right now on the fastest supercomputer list. Is about 2.4 million cores. And even if you use this type of machine, the type of simulation that you can actually realistically run are of the order of 8,000 cube particles or cells in this case. And this means that we're about 11 orders of magnitude away in terms of resolution from being able to resolve the full dynamical range that we wanted to. That's the first problem. Now you could say, okay, well, sure, we're away, but computer gets fast and faster every day. There is this thing called the Moore's law that you're probably all familiar with that tells us that computational power doubles every 1.5 years. Now I'm not going to go into the discussion of is this law going to last, is going to stop in the next years or so. Let's assume that it will continue going with exactly the same trend. This trend is shown here for the last 50 years. This is the number of transistors in one of your CPUs, and this is actually showing some interesting features of technology that we can ponder for a second. One important feature is that the frequency of your CPUs inside your laptop is pretty much been constant for the last 10 years. It reached something like a few megahertz, and now it's very hard to make things that are working at higher clock rates. At the same time, the single thread performance also stalled. And what's actually compensating for these technological problems that relate to miniaturization is the fact that we're actually now able to put more logical cores in your CPUs. So your typical laptop now contains 4 to 8 cores, when in 2000, in the years 2000, you only had 1. So let's assume that this trend will continue going. Then you can try to determine how long it's going to take before we can run the first direct numerical simulation of the convection in the sun. And that number is 10 to the 11, is the order of magnitude what we are away from the type of calculation we want. This is the doubling, and so it takes 55 years. So this is going to be another 55 years before we're going to be able to run this type of simulation.
It's not so bad.
It's not too bad if it wasn't for the fact that this simulation means that this is the simulation on a dynamical timescale. So this is if you want to simulate a few turnover timescale. The turnover timescale in the sun is of the order of half an hour or so. Now the problem is the sun doesn't leave for half an hour. It leaves, that's the timescale it takes for a sound wave to propagate through the sun. But the sun reestablishes its structure not only hydrostatically, but also thermally. And that takes a much longer time, the Kelvin-Helmholtz timescale. So for the sun to stay and reach a thermal equilibrium, you need 10 to the 7 years. And the most important timescale for a star is actually the nuclear burning timescale. So when you move from one fuel to another, and so then you will, for example, the sun will leave about 10 to the 10 years, 10 billion years burning hydrogen. Then there will be a thermal phase where we'll settle into a different type of burning, hydrogen in a shell, and then we'll move to burning helium in the core, and so on. And so that's moving from different time scale. And you want to resolve all of them. And the problem is that if you want to do that, then you actually have a very, very large number of time steps as well as cells. And so that's what it takes to run the sun on a dynamical time scale, on a thermal time scale, and for the full evolution. There's going to be more than 100 years from now, assuming a Moore's law, before we're going to be able to run a direct numerical simulation of the sun for the full evolutionary life. Of course, there's a few caveats to this discussion. One is, well, this is assuming the same algorithm and the same way that we resolve, like Navier-Stokes equation and in numerical simulations. The other thing is that you might say, well, we don't really need to run the sun for a full evolutionary timescale. We just maybe need to run certain specific key evolutionary phases for long enough time to capture the fundamental important physics. And that's actually one of the main arguments that I'll try to make later of why simulations are still very useful, despite the fact that we cannot run the full calculation. In fact, I think that models are still useful, even if you don't run the full simulation for the extended time scale, but also not down to the scale of dissipation. You can still rely on the trends and on important physics that you might understand in the simulation. For example, we do still run simulation of stars in 3D, where we cut down your turbulent cascade of some scale, meaning that we can only do a simulation which is not resolving the full turbulence. But you might still hope that some of the results might give you the right direction and the right understanding of the fundamental physics that it's important for that specific object. Particular attention needs to be taken to MHD calculations, because in the presence of magnetic fields, you can have things like inverse cascade that can connect the small scale to the large scale. And if you don't resolve the small scales, then it can be a problem. OK, so this is the type of loop and synergy that I was hinting at earlier on. We have these high-precision big data sets that are now provided by missions, especially space mission. We see Gaia here, Kepler and TESS. We have 3D calculations, yes, unresolved, yes, run only for specific phase of evolution. But if we couple them with the good old one-dimensional calculation, that we compare the results of these studies with real stars, and we iterate. Every time we find a discrepancy, we try to understand a little bit better what the right physics that we're missing and how to implement it back in 1D. Then this loop, this cycle might converge, hopefully, to a better understanding of stars. And that's, I think, where this era, where the power of this new era is. OK, so with this in mind, I want to talk a little bit about a few open questions and problems that I have been working with some collaborators, and thanks to a community of other people in the last, I would say, 5-10 years on. And we'll start with some open questions regarding rotation inside stars, so internal rotation and internal magnetism. So we'll talk about things like differential rotation in stellar interiors and the magnetization of the plasma in stellar interiors. Now, all this talking of stellar interiors might sound crazy, and especially if you have in mind this famous quote from Sir Arthur Eddington, who in 1926 famously said that he believed basically that we will never be able to probe the interior of stars. What he believed was a world where theory will reign sovereign, and basically all you can tell about stars is something you can determine from fundamental theory. And so if you do your theory right, then you will be able to know what's inside stars. It turns out that stars are very complicated, and there's a lot of physics going on. So even if you are very good at doing theory, sometimes having a way to check what's going on is a good idea. And this way to check came available only in the last few years, thanks to space photometry through asteroseismology. So asteroseismology allowed us to probe and observe the interior of stars for phenomena like rotation and magnetism. And that's something I will talk about in the next few slides. So the real revolution happened with Corot, but most importantly with the Kepler Satellite. So the Kepler Satellite observed thousands and thousands of stars and observed these stars oscillating. This is a byproduct of looking at a lot of stars, waiting for a planet to pass in front of it. You have to monitor the light of these stars with very high precision for a long time, in the case of Kepler for 4 years. And it turns out that stars don't just stay there. We knew that for the sun. The sun has this solar oscillation, which is an oscillation of the outer layer happening with a period of about 5 minutes. The sun, every 5 minutes, moves at about this velocity, about 15 centimeters per second. And where is this oscillation coming from? Basically, the turbulent convection in the envelope, the one we were talking about before, creates some noise, if you want, that knocks some resonant frequencies of the other region of the star, and the stars start oscillating. This is a stochastic excitation process that allows the sun to oscillate in many, many different degrees, harmonic degrees of oscillation. So L equals 0, 1, 2, and 3. So the radial, dipolar, quadrupolar, octupolar, and so on, up to very, very high L. And we can observe those in the sun because the sun is resolved. But before Kepler and Corot, this was the situation in terms of how many stars in the sky we knew were actually pulsating through this mechanism. There was just a handful of them. And it was very, very low precision determination of this oscillation. As soon as Kepler went up, the situation changed abruptly. And this is the situation as of 2016. Each one of these symbols is a star oscillating in solar-like oscillation, so where the star is oscillating because of the stochastic excitation mechanism. So what is this type of oscillation and what kind of waves do propagate in the star? So this is going to be the most technical slide I will show today. I just want you to stay with me because this is going to be very helpful to understand what's coming later. This is a technical diagram called a propagation diagram that shows basically shows which waves propagate in which part of the star. And it shows the radius of the star on the x-axis in a log coordinate, and some characteristic frequency in microhertz on the y-axis. The fact that we're talking about microhertz frequency is already telling you that this oscillation in the case of giant stars are going to happen on very long periods of weeks to months. And that's a characteristic of a bigger star than the sun oscillating. It's a bigger musical instrument, so it makes like lower frequency sounds than the sun. So I'm showing here now two characteristic frequencies. The lamp frequency is the blue curve, which is basically nothing else than the inverse of the sound crossing time through the star. So this is telling you the frequencies of P modes. P modes can live only above this blue line and this red line, which I'm going to tell you in a second what they are. So if you excite the star via turbulent convection down here in the outer region of the star, then you can have P modes propagating down to this blue line and coming back. That's a P mode cavity. The G mode cavity is determined by this red line, which is the Brand-Vasila frequency, which is basically nothing else than the frequency of the oscillation of a piece of plasma, which is displaced around its equilibrium point in a radiative region of a star. So you go in a radiative region of a star, you just push the plasma down, and it will just oscillate back and forth at the Brand-Vasila frequency. So this is actually the region where internal gravity waves can propagate. So internal gravity waves, or G modes, can propagate below the red and the blue line. So in a sense, the star at the frequency of 10 microhertz is divided in three regions. A G mode cavity here. This will be the core of the star in this case, you can see. A P mode cavity, and then there is a evanescent region. Here some wave power can propagate, but it's evanescent. So if you think in terms of eigenfunctions, the eigenfunction is exponentially decaying in this region. You can still have energy going from here to here or the other way around, but you have to go through a tunneling integral. It's very similar to a tunneling integral in the context of quantum physics. Now, if you have a star and the star is convective up here, you can excite P modes. It's very hard to excite G modes because all the energy is deposited here. Okay? That's the case of the sun, if you want. Now, if you go to a red giant star, the red giant expands. The frequency of the turbulent convection at the surface decreases. So in a sense, you're moving up the frequency, the turnover frequency of your excitation mechanism, and it goes up here. And you see what happened, that the distance between these two lines decreases, so that at some point, the instrument which is in the core of the star, this drum that nobody was playing before, can actually be played by some of the energy leaking from the P mode in the P mode cavity into the G mode. So in a sense, you can get to a situation like this, and this happens for red giants, where some of the wave energy leaks into the core, and it creates an oscillation, an eigenfunction, an eigenmode, which is made of two parts, a G mode part and a P mode part, plus a little evanescent region, evanescent component. This is called a mixed mode for obvious reasons. Yes?
So is this only the structure if you have a radiative core and a convective envelope?
Correct. So this will be the structure for a red giant, where we have a radiative degenerate core and a convective envelope. You can imagine a very similar structure if the star is burning helium in the core, for example, on the red clump. The red clump is very similar, with the difference that now we have a region here which is convective, so no G modes can propagate there, but it's still going to be a G mode cavity above it and the P mode cavity on top of it, and the envelope is still convect. In fact, mixed mode also exists in red clump stars. just that the frequency of the G modes here is going to be slightly different because the G mode cavity is going to be different. And you can actually tell that if the star is in this phase or the other by something which is called the period spacing of the G modes. So that's one of the tools that you can use with asteroseismology to determine the state of burning of a star in that case.
I was thinking, I guess, of the sort of the flip side where you have a main sequence star.
Yeah.
That's higher mass, so it has this sort of flipped.
Right. So in a massive star, during the main sequence, there is a convective core here and a radiated envelope mostly. And so the idea is that you maybe can excite G modes like and running wave on top of the radiated layer, and they maybe can propagate to the surface. That's actually more like in the domain of massive stars, and it's still debated if we are able or not to see those. Yeah.
How do you get the burn by stellar frequency to overtake the land frequency?
Say it again?
How do you get the Bragg by stellar frequency to overtake the land frequency, the sound wave?
To overtake.
To be faster. I would expect it to be
Always.
always. Yeah, so I'm just curious if there's something.
Well, so there's two components to the Brandt. There is a thermal component and there's a compositional component. So this part, usually this peak here, is due to the compositional component, which is really increase the Brandt at that location. So you can have very high peak of the Brandt, almost arbitrary because of the existence of glitches in composition. Okay, so the existence of these big mixed modes is very important because they propagate both in the core and the envelope. And so they can allow to determine properties differentially of core and envelope of evolving stars like red giants. The first example of where this was really used is the case of determining helium burning from hydrogen shell burning star. But the second one that I'm going to focus on is the ability of using them to determine the rotation rate of the core as compared to the rotation rate of the envelope of stars. It turns out that as this star evolved during the red giants, the core rotated about 10 times faster than the envelope. This was the main result that was kind of unexpected. Reason being that if you assume that the core is contracting, as it should during the evolution of the star, and the envelope expanding, the core should spin up substantially during the phase in the absence of any angular momentum transport. So if there was angular momentum conservation in the core will spin up substantially up to a factor of 1,000 respect or more respect to the envelope. But this was not observed. So the observation instead, and this is a plot showing on the x-axis the radius of stars. So each one of these crosses is a star observed through asteroseismology on the red giant. Forget about this clump stars here. Just focus on this. And this is the average rotation rate of the core. You can see that, interestingly, as the star expands, the core is not spinning up. It's actually spinning down or staying mostly at the same rotation rate. That was a big surprise. That was not what people expected. And so the question was, can we reproduce this? Do the 1D stellar evolution models that we have, for which we calculate the evolution of stellar interiors down to the neutron star and black holes, where we then predict their rotation rate, for example, do have the right ingredients such that they can predict the rotation rate and the rotation evolution of these stars. So that's something we did because many of these stellar evolution calculations do have included prescription for angular momentum transport by a number of processes. And I'm just going to give you a little bit of a laundry list of what people usually do. Usually we have hydrodynamic instabilities, like things like shear or meridional circulations, so that can transport angular momentum in the radial direction. We have magnetic torques implemented in different flavors, where you can have a magnetic field. You can imagine magnetic field very simply as a rubber band, and if you wind it up, it's gonna give you like a restoring force to try to decrease the amount of shear that initially wanted to wind it. And finally, we also have internal gravity waves. I was discussing internal gravity waves transport energy, but also angular momentum. And depending how they get dissipated, they can transport angular momentum non-locally through the star, which can also try to restore a state of more rigid rotation with respect to differential rotation. Obviously, there's a lot of assumption made by people who came up in the past, like 34 years with recipes to implement this complicated multidimensional processes in 1D. Usually, these are implemented in diffusion approximations, which have a lot of caveats. And so we wanted to see if it was possible to reproduce these observations with the models. So this plot shows first result from a theoretical one-dimensional calculation of red giants evolving on the red giant branch. You can see again the radius of the star as the star expands. And this is again the period rotation of the core. First, the black line is just the envelope. As you expect, the envelope has a lot of inertia. It's big. It's just expanding. It doesn't really care about angular momentum transport, in fact. And what it just does is, at the surface, you will see mostly the envelope evolving as r squared. That's the period up there. Then the core, the evolution of the core, depends on the type of angular momentum transport that you are putting at work. So the green line is the pure angular momentum conservation. So if you let the core just contract without exchanging any angular momentum with any other regions of the star, as I said, you expect a strong spin-up effect such that the core and the envelope are almost 3 orders of magnitude away from each other. The purple one is showing what happens if we account for things like shear and meridional circulation. They do help a little bit, but actually their timescale is much longer than the timescale of the red giant evolution. So they cannot actually catch up and transport enough angular momentum into the core, outside of the core. Finally, the red line, our best hope, so to speak, is the result implemented using this theory of Taylor's fluid dynamo that allows to calculate internal magnetic fields and resulting torques in stars. And this one allows to couple much better the core and the envelope. But how well do we do compared to the observations? Well, not very well. So even our best bet or the most efficient way we had to couple core and envelope in these stars resulted to be like at least 1 order of magnitude too weak. So this pointed to a either much more efficient way to couple the core with the envelope, or maybe some of the assumption in the way for example, we treat angular momentum in the convective envelope to be wrong. For example, it could be that there is a lot of angular momentum, there's a lot of differential rotation already in the convective envelope that we haven't account for in the models.
Can I?
Yeah.
I think another assumption that's underlying all of this, because it's built in MESA and many codes, is cellular rotation.
Sure.
And that assumes very efficient horizontal transport.
Yes.
But it's never specified exactly what it is. And you could imagine a situation where it might vary whether you're in the sun or going through red giants.
Yeah, so the point here is that to run a star in 1D, with rotation, there is this thing called a shallow approximation where one assumes that above a horizontal shell, so isobars in the star actually, you assume that there is some horizontal turbulence that's very efficient to mix both angular momentum and composition on the time scales of your time step, so that every shell is basically homogeneous in J and composition. And so that way you can collapse the latitudinal coordinates just on a radial coordinate and run the star as a 1D model. The question is this approximation good or not? If it's not good, then we cannot run 1D stellar evolution calculations the way we do. People have looked into this. There's a lot of literature. I think there are some reasons why that assumption is not bad, but the details, the devil is in the details, I agree. And so usually the fact is that it's much easier to make stars obviously on a horizontal direction, And there are these things called baroclinic instabilities that develop if you have a star where it starts rotating. And those act very rapidly, usually on dynamical time scale. That's usually very short compared to the time step in your calculation. So that's usually the story that is told. But I agree, it's more complicated than that.
And I have a question about the Taylor spruits.
Yeah.
Can you reproduce a sun with Taylor spruits? Because obviously a test is, can I get the sun right?
Yeah, yes.
And does it work?
Yes, yes. Historically, that's, the test of a Taylor sprut has been the sun and the final rotation rate of compact remnants that were kind of in the right-ish ballpark. But I think this was the biggest failure yet for that theory. And that's why people have looked again into some of the details of a Taylor sprut dynamo. So that's what I'm hinting at here. So this is one of the results. The fact that internal angular momentum transport was not fully understood, as we thought at least, or at least not as good as we thought. And so this large coupling between core and envelope seems required, which has important consequences for the rotation rate of compact objects, for example, for the spin rate of LIGO black holes. If this is true, as we believe it is, then the prediction is that classic evolution of binary stars without later reaccretion should lead to black holes that are very slowly spinning with A-like spin consistent with 0, basically. So this led to Jim Fuller and some collaborators to look back at this at the saturation regime of the Taylor sprut dynamo, and actually they revised it and came up with a theory that actually can reach larger magnetic field and stronger coupling. And if you, it turns out that actually that theory now works fairly well to reproduce the observation. And so I know that Jim is going to come here, so I'm not going to steal his thunder, and I'll let you guys let him talk about it. I think he's going to be here in a couple of weeks, so you can ask him all about it. But I think this is an interesting development and something that I'm happy because all this asteroseismology is pushing people to look back at this assumption and trying to revise some of the existing recipes. As I mentioned, there's also the possibility that there's a large amount of shear hiding into the convective envelope. Unfortunately, it's very hard to measure. You cannot invert things like do in the sun. The inversion in the sun is possible because we have very high L that we can measure. For stars that are not resolved, you can basically see up to L = 3, and only a limited number of modes, and so it's very, very hard to do an inversion. There's been some attempts and some tentative evidence of strong angular velocity gradient at the base of the hydrogen burning shell, which seems to maybe point toward this picture to be potentially correct, but I think the jury is still out.
I think we should also be careful about drawing implications about this beautiful asteroseismological work on the subgiants, the early giant branch to the tip of the giant branch, which is most relevant for rotation of compact remnant.
Right. So the tip of the
rotational properties are very different.
Right. So most of the measurements are only available for early on the red giant. You cannot measure things later on, and the reason is that later on, basically, you have no coupling between the core and the envelope, so it's very hard to measure rotation rate of the core.
You did have the horizontal branch or red clumps, but
yeah.
In that at least you know both pre and post. But
yeah. Yeah. No. Absolutely. Yeah. You're right. So you know that. Exactly how they got there, we don't know exactly, but yeah, there has to be some angular momentum transport. Yeah. Okay, so want to switch gear and move to a second puzzle, still related to asteroseismology. So it turns out that out of these stars that show mixed modes and L = 1, mixed modes, and there's a group of stars called depressed dipolar modes. So what are these stars? So what I'm showing here is as function of the frequency of maximum power. So this is a proxy of evolution. Stars move from here or in the early red giant branch to down here to the tip of the red giant branch. So the star expand, they move down to lower and lower frequencies. You know, the star is getting bigger and bigger, bigger instrument. And you can see that each one of these points is actually a star. And what I'm plotting here on the y-axis is the visibility square, which is a measure of mode energy. And here is only showing L equal 1. So that's a dipolar mode. The dipolar mode is actually are the modes that actually couple better with the core. That's the reason is that higher L means a larger evanescent region because the lump frequency is actually higher and higher. And so most of the mode energy is transferred from the P modes into the G mode. So these are the ones that couple better with the core. And it's interesting to see that for star, almost at the same point of evolution, you can have objects that either stay on this branch, which we call the normal star, where the mode energy is normal, and stars that lay down on this branch, which are called the depressed dipole mode stars. So the interesting thing is that for each one of these stars is completely identical for all the other modes, L equals 0, L equals 3, except for these L equal 1 modes that are depressed. So whatever is happening to these stars is something that's happening in the core. Because as I told you, the L equal 1 modes are the ones that probe the core, while L equals 0 doesn't, and L equal 2 couples very, very weakly. So we have to try to figure out what's happening to these stars with a couple of hints. One is this thing that has to be something related to this stellar core. And then also with this fact that if you stack stars as function of their mass, the fraction of depressed dipole is basically 0 for stars less than, like the sun, or less than 1.1 solar masses, and then increase going up in stellar mass. So what we came up with is a theory, basically, where we believe that the culprit is strong internal magnetic fields hiding in the core of these red giant stars. Now, what is a magnetic field doing to the incoming gravity waves? Well, the idea is that as you have internal gravity wave propagating into the core, internal gravity waves want to displace the plasma mostly horizontally. Now, if there is a magnetic field line inside the core, as the internal gravity wave comes, it just wants to bend the magnetic field line as well. Now, if the magnetic field line is weak, meaning the restoring force, the Lorentz force, is weak, then the internal gravity waves would just go and move the plasma in the field. However, there is a critical magnetic field where the Lorentz force becomes comparable to the buoyancy force, which is the restoring force for your internal gravity wave. And at that point, your wave has to be affected. And so the critical field strength can be written out. And it turns out to be dependent on the Brandt, the frequency of the wave, and the density. And it turns out to be of the order of 10 to the 5 Gauss. So if you have a magnetic field of 100,000 Gauss into the core of these stars, you can efficiently remove energy from the mode, because as the internal gravity waves come onto this magnetic field, it's actually transmitted into Alfvén waves. The Alfvén waves have a much higher wave number, and they tend to dissipate. So all the energy that you leak into the core is lost. It never makes it back up to the surface. So your P mode is pumping energy into the core, and so its amplitude is lower because it's losing energy. The energy never comes back. So we interpret then the star that show these depressed modes as stars with internal magnetic field in excess of 10 to the 5 Gauss. Now, if you try to interpret this plot that shows the fraction of stars with depressed dipolar modes as function of mass, another very interesting thing pops out. Stars with masses less than 1.1 solar masses do not have any suppression. And these are also the stars that didn't have convective cores during the main sequence. Stars that do have masses above 1.1 shows an increasing fraction of depression, so to speak. And this is actually the dividing line between stars with convective cores on the main sequence and starts with radiative core. This is the transition from PP dominated to CNO dominated hydrogen burning in the core. And the PP and the CNO is much steeper, depending on temperature, leading to convection.
When you say 10 to the 5 Gauss, you're talking about 10 to the 5 Gauss at the burning shell? Or?
Correct. So below the burning shell, and so the idea is that I wish I had a propagation. I wish I had a Propagation diagram, but the idea is that you have this convective core, and inside the convective core you can have a dynamo, like where you can reach equipartition between convective energy density and kinetic energy density and magnetic energy density. That can easily give you equipartition field of 10 to the 5 Gauss. There's simulations showing that. That flux is, if it's conserved in some stable configuration, then you can easily get 10 to 6 or even 10 to 7 Gauss on the red giant. Now it depends a little bit on the geometry of the problem or the star in terms of structure. So for example, Chris, you asked me about where this magnetic field will be. Well, it depends on the mass of the star. For example, if it's a, say, 1.5 solar mass star, this is the convective core doing the main sequence. And then there's going to be an hydrogen shell burning. And then there's your convective envelope up here. This is all in mass coordinate. And this is, let's say, time. And so, you know, in this case, one can imagine that the magnetic field is kind of confined to this mass coordinate. Okay? So there will be a magnetized region below this mass coordinate. And the assumption is that the field doesn't really move if it's in a stable configuration because the ohmic diffusion timescale is much longer than the timescale of evolution involved here. Now, the relative size of this and the relative, like, later burning by freshly produced helium from the hydrogen burning depends on the mass of the star.
And I recall, though, that it's more massive than 1.6 solar masses, where the final white dwarf remnant has a mass equal to the mass of the
Correct. So something I'm going to talk too much about now, but is that also this ramp up, we believe, is due to this fact that the more massive the star, the main sequence, the bigger this convective core, and less burning effect of the hydrogen shell.
Okay, but I don't remember the number off the top of my head. For 1.6 solar mass progenitor, what is the mass of the main sequence convective core?
Yeah, I don't remember. I have the plot of that. I can show you later. Yeah. But yeah, so the idea is that if this magnetic field are conserved down to the white dwarf, the prediction is that this mechanism will lead to more massive white dwarf being most likely magnetized, which is consistent with some of the observation, but that's not the only channel that can do that. So
this is a deterministic process. Every star is the same except for mass.
not really. There's rotation, for example.
Every star pretty much rotates the same way.
Well, for example, if you think about, you know, like stars up below, so there's this thing called the Kraft break, showing that star on the main sequence, they rotate rapidly if their mass is about 1.2, 1.3 solar masses. Below they have convective region that spin them down.
So that function of mass again.
Well, no, and then above there is a distribution. If you look at the distribution of stars in the main sequence, there is, for example, A stars. They have a distribution of rotation rate at the surface. We don't really know what's in the core, but let's assume they rotate rigidly. There's going to be a distribution of stars with different rotation rate. And that means also distribution of Rossby numbers, which might lead to a distribution of efficiency in generation of magnetic fields.
Your main fault, or is it the other thing, I guess, that you sort of showed on your previous plot, that you have some kind of random configuration of magnetic field?
Yeah.
Not at all guaranteed to not the stable.
Yeah. That's the other big question. What happens when this region shrinks enough and then the magnetic field is left alone with some magnetic energy and helicity? Then you want to reach a stable configuration. If you don't, it's game over. You know, your field just move in a half in time scale. If it does, when it does it, you know, and people have done simulation of these and see that sometimes you reach this configuration, but maybe sometimes you don't. And so in that sense, it's not deterministic. It might depend on things like, you know, like your magnetic helicity, and we don't know that yet. Anyway, let me move on, and then we can talk about this more later. Yeah,
I think what should also keep in mind that this doesn't necessarily imply that for this range of masses that you will have a very strong magnetic white dwarf, because the other mass shells of the white dwarf in this progenitor to mass range will be assembled later on.
Yeah, absolutely. There's a lot happens later on to star, and that I haven't talked about. But on the assumption that somehow the magnetic flux is conserved, then you can have a magnetic field that will show up as magnetized white dwarfs.
Well, it's conserved outward.
If it's conserved within the, so if like the shell, like the mass coordinate of the star, the magnetic field is not evolving on omega diffusion timescale much. What it does is it can only be destroyed or from out of its equilibrium configuration. Otherwise, the flux will be conserved.
You have the convective zone coming down, right?
If the convective zone coming down,
That mass shell, then what matters later is whether the convective zone is able to sustain that.
right? So you might either amplify or destroy it, and that will depend on the relative efficiency of kinetic energy density in the convection zone, respect to, for example, magnetic energy density that you have there. And so I think that you can have,
We should talk about
yeah. So we talk about that in a recent paper with Jim about it. But let me move on, otherwise I'm not going to be able to finish. Okay, strong core magnetic fields potentially ubiquitous in stars above 1.5 solar masses. So if this connection between suppressed dipole modes and magnetic field is true, then one prediction is that potentially a lot of massive stars might have magnetized cores, at least during the main sequence and after. And what the effect of this magnetized cores is on the evolution of the star in terms of angular momentum transport later on. And even like in later phase of evolution, if these fields are conserved, this can be quite important to determine the properties of the remnants, as we just discussed. And I want to say that these magnetic fields are definitely not included in stellar evolution. So that's something to keep in mind. Okay, so I want to use the last few minutes I have to talk about massive stars, which is basically something I work on a lot. And in particular, I want to talk about the evolution of massive stars, and I want to don't need to make a case that this is interesting. There's a lot of outcome of massive stars that are of very, very of astrophysical importance, going from supernovae of different type, luminous blue variables, obviously the progenitor of compact remnants, and gravitational waves. So this is the message I want to get across is that massive stars are extremely uncertain. The evolution of massive stars is extremely uncertain. We still don't understand them. And this is my laundry list of what the uncertain physics is. I will talk now about stability and energy transport and mass loss. I just mentioned, rotation and magnetism. Although it was in the context of lower mass stars, I think that what we learned from asteroseismology of low mass stars can be ported for more massive objects. The final rotation rate of more massive objects that make neutron stars and black holes is extremely important if one understands things like long gamma ray burst and maybe superluminous supernovae. So that's why it's important to understand if our 1D diffusion approximation of this angular momentum transfer mechanism is correct. Finally, binary interactions. Okay, so you probably heard that the majority of massive stars are found in binary systems, or actually multiple systems. So binary interactions are going to be very important, and every massive star will probably have one or two interactions during their lives. My point is that my tendency was that initially I started working a lot on this, and then I realized that since the physics of even single massive star is so uncertain, I think that it was going to be very hard to come up with a full picture of massive star evolution, adding the fact of binary interaction. And the reason is that every time you have a star interacting with a companion, the interaction is usually fairly short. It's dynamical and complex, and leaves behind basically one single massive star. So after the interaction, maybe the binary expand orbit, and then the stars are changed in property, but they're still going to evolve most of their life as single stars. So if you don't understand what they do as single stars, there's no hope that we can, add the more complex physics of binary interactions. So, I think that it's important to keep that in mind when we look at binary evolution simulations. So something I think it's very, very important for the massive star is mass loss. And how that connects to the stability of the other layers is what I'm going to talk about now. In terms of mass loss, there are basically 3 mechanisms for a massive star to remove its outer layers for single stars. Obviously, binaries can also do that. One is line driving winds. During the main sequence, the star is hot. You can drive a wind through line driving. This is actually the part that we understand the best. There is a theory for this. It's well motivated, and it has some good prediction that have been tested. Uncertainty of a factor of a few. But the problem is that most of the mass is actually lost in other evolutionary phase of star, not in the main sequence. In particular, when the star becomes cooler, red supergiants or yellow supergiants, these actually, the school winds are poorly understood. So we don't have a theory that is able to predict the amplitude of the mass loss in this phase. We don't even know if this is metallicity dependent, for example. And finally, there are continuum-driven winds and eruption that we do see. We do see LBVs removing large quantity of materials from their envelope, and we really don't understand what's going on. What is the process that drives these things? So what I'm going to talk the last minute is the simulation of the other regions of very massive stars that we believe is potentially interesting to understand what kind of driving, what kind of mechanism is behind luminous blue variables, which are these objects, massive stars that seems to shed a lot of material, and they're very luminous and obviously variable. One key ingredient to understand what I'm going to show you is the fact that in the outer region of this star, massive stars, we have those large radiative flux, which is encountering cooling regions where the opacity is going up. So this is a key ingredient to create super-Eddington regions. The flux wants to go out, and the opacity goes up as well, so the region becomes super-Eddington. The first thing the star does is turn on convection. The problem is that those regions, by being a cooler temperature, are also very close to the surface. And in this situation, convection is highly inefficient. So in one-dimensional calculation, again, when we have convection, we use the 1D MLT theory. What is the MLT theory? You take like a parcel of material, we put some energy, and you carry it around about 1 mixing length, which is a fraction or multiple of your pressure scalite, and then you remove your energy and you go back. And you do this with some speed. Now the problem is that in the case of this region, the advection timescale, so the time it takes to move the cup back and forth, becomes comparable to the diffusion timescale of radiation, meaning that the content of your cup leaks out of the cup as you move it. So by the time that you end your path, you lost all the energy you wanted to transport. This is the case of superadiabatic convection or inefficient convection. And it turns out that in these regions, if you want to do a good job on understanding how the energy is transported, you need to understand the interplay between turbulence, radiation, propagation, and the opacity. And so that's a regime where you need to calculate radiation hydrodynamic simulations of the region. The key ingredient is the opacity, as I said. As you're going from the core of the star where everything is ionized to the surface where hydrogen first and helium and hydrogen ion and then helium and hydrogen recombine, you see an increase of the opacity. The opacity not only depends on the temperature but also on the density. So each one of these lines represent opacities for different denser and denser regions. So you can see that if you're at the helium, for example, and you're a difference of density of factor of 10 implies also a difference of opacity of a factor of a few. obviously, opacity also dependency on the dependent on the metallicity, especially ion opacity peak. So that's important if you discuss, for example, population tree stars. So, okay, so I'm going to show you the three-dimensional radiation hydrodynamic calculation of luminous blue variables, calculated using Athena++ code. So the idea is to try to understand these LBV stars. They observe to stay in quiescence on this hot asteroid instability region, and sometimes they move to the cool region, they start shedding mass, and then they go back with cycles of order of timescale of 1 year or so. When we simulate with 1D stellar evolution calculation, it's very hard to make prediction depending on the details of implementation of energy transport in the envelope. You get very different tracks. So we decided to run calculation, initial calculation with 3D modeling. And so this is the calculation. We start with a structure coming from a 1D model. So we just put like the flux coming out of the core. We remove the core. We just simulate the envelope. And what I'll show you, it's about a month and a half or two of evolution of the star. As you'll see, I'll show you the gas density. Time is here. So the star, the envelope settled into a turbulent state very rapidly. The ion opacity peak is down here, and then the helium is higher up in a lower temperature. And you see that as soon as the star reaches a steady state, some outflows begin. These outflows it's pretty stochastic. We see that there are plumes that are ejected locally. Some they actually made it out. They're faster than escape velocity. They're unbound. Some actually they fall back. There are shocks. Interestingly, this continues. So even in steady state, we keep having these features. And as I'll show you, these are driven by the large radiation pressure, radiation acceleration in the envelope of this star. The mass loss rate that we measure, looking at how much material is lost from the system, is on the order of 10 to the minus 5 solar masses per year. And here we're not even including line driving. This is just purely from continuum. Yes?
So previously, the comparison of the Krumholtz et al. Flux limited diffusion with the Yang, Stone, and Davis closure scheme.
The variable Hamilton tensor.
Different results as
Yes.
Yes. Can you comment about how your method compares with
this is a variable Eddington tensor, so this is exactly the same that Stone and Actually, this is done with Jim Stone and Yanfei Zhang.
Oh, that's the same.
Yeah, it's same. Yeah, but you totally. So the point is that depending on how you treat the radiation scheme, that can lead to very different results in the coupling with matter, and you can have spurious results where you drive or not an outflow depending on what scheme you used. Particularly M1 and is not the best. Anyway, so now I show you that this is interesting to reproduce this type of outflow, but I haven't explained at all what's happening in the simulation. So this is what the last thing I want to say. So what we figure out is the role of coupling between the radiation-induced turbulence and the opacity in these horizontal layers that are calculated in this simulation. So what happens is that luckily you have radiation, you have like your turbulence leading to density perturbation in the region above the ion opacity peak down here, where actually helium recombines. So at the region where helium recombines, we can have a situation where the density fluctuates a lot. So if you imagine that your luminosity is such that you're slightly below Eddington for your average density, but then you have a plume which has like a higher density. All of a sudden, that plume feels super Eddington, so feels the radiation acceleration of the radiation force being larger than the gravity, and so this plume finds itself to be accelerated outward. And so the stochastic excitation of density fluctuations couple through the opacity to the radiation field in a way that drive ejection of material from the star. And so obviously this was something that you cannot capture in 1D, where everything is collapsed to an average opacity. And so the trick was really resolving the radiation-induced turbulence coupling with the opacity, which is something we did by coupling the Mesa code module for the opacity to Athena++ and the variable Eddington tensor method. Yeah, so it's showing that we're in steady state, and there's some actually prediction that we can use to test this idea. This simulation predicts that the star should have some certain variability with certain time scale that depends on the star being in outburst or in quiescence. So in outburst, the variability is much larger amplitude but shorter time scale compared to the LBV in quiescence, which have much smaller variability but on longer time scale of weeks or more. And this is something actually, it's a prediction that is tentatively been confirmed in some observations. But I want to finish here just reminding you that massive star evolution is still very uncertain, even for single stars. And there's some stride we've been made in trying to understand LBVs with the first 3D global radiation hydro calculation, establishing that the interplay between the helium opacity and radiation turbulence can lead to outflows and potentially a way to understand some LBVs. And I would like to stop here and thank you for your attention.
All right, so we had a bunch of questions throughout the talk, but we have a couple of minutes for any other questions if folks have them.
Yes.
The simulation, you started telling us how it was hard to simulate the turbulent cascade in the sun's convection zone. So the obvious question is, can you convince us that you capture just a large scale that's enough, or should we worry about the small scale ruining the...
That's a great question. So yeah, as I reminded myself that I shouldn't believe too much. So I talked to Jan-Fei about this, and the idea was to run a little bit of few stuff. So we didn't start with the global simulation, by the way. We have a couple of papers on local box simulation where we can also do a better job in studying how this changes as function of resolution. So we have some resolution studies trying to see that qualitatively things don't change too much. It's very hard to make a claim that, going down much more, you would not see a change in behavior. Jan-Fei believes that this should be a solid result. But I don't know. If you had the density fluctuation here being much smaller scale, will that change the way you drive things? I don't know. I mean, collectively, you can imagine that there will be more holes in your regions, but maybe you'll still be able to drive smaller blobs that then merge. And
isn't there a scale in that problem that is basically the optical thickness of a gas element, and that's a large enough scale that you think it is?
Yeah, so that's true. That's true. Like I think that the change in optical depth that you have so the fluctuation that we see are fairly large. So we have, but so would that change in MHD, for example? We do see that in the box simulations. So magnetic field can have a role in there. And I think that what we're suggesting here is that is a mechanism that we believe plays a role, but the quantitative answer, I think it needs to wait for more calculation and more study.
Any other questions? Let's thank Matteo one more time.